because it's been like a week since I've seen you. This is what we learned on day 1. So this was our small, medium, large side, small, medium, large angles. Does it make a triangle? What are the possible lengths for the third side? Is it acute, obtuse, right? All that jazz. So just a refresher with that. So our first part here, our smallest angle is across from our smallest side, medium across medium, large across from large. Likewise, we can go opposite. So if I know my smallest side is 2, that's JL, the angle. Smallest would be angle K. Do we have questions on this first chunk here? The biggest mistake students make is not following directions. So make sure you answer what it's actually asking for. Also make sure you have proper notation, angle notation, the segment notation. All right. Then to decide if it makes a triangle, the theorem says any 2 sides have to add up to be bigger than the third side. Now we said our shortcut we can use is just check small plus medium is bigger than large. Do we have any questions on this part? Awesome. Then on the back side, again, the theorem is that any 2 should add up to bigger than the third, but again, our shortcut, our shortcut we said is that to find the possible lengths for the third side, we can simply add, that gives us our upper bound, subtract, that gives us our lower bound, subtract in such a way that you get a positive value. And then I just went ahead and wrote this in on the side because it didn't have any problems that actually address this, but the other thing that we learned on that first class was that Pythagorean theorem says a squared plus b squared equals c squared. When it's equal, we know it's a right triangle. If it's a right triangle, it's going to automatically satisfy this. But in the event that it's not equal, if c squared is bigger, that's obtuse. C squared smaller, that's acute. Make sure you are doing squares. Every year I have someone that just does a plus b compared to c. You have to actually do the squares of it. Okay. Yes?
Do you have Scantron quizzes?
I almost have all my absentees. I made it up, so next class you get them back. And I think I now know where a working Scantron machine is, because the one that we have is broken. All right, now our small, or our bottom ones here. This is similar to a couple problems we had in our textbook homework. It says identify the smallest segment in each diagram. So we want the smallest overall. Now remember that theorem, small, medium, large, you can only use within one triangle at a time. So I cannot take a look at my first picture here and say, oh, the smallest angle in the whole picture is 28 degrees. Because again, I can only look at one triangle at a time. So I'm taking a look at my triangle on the left. I label small, medium, large from there. Take a look at my triangle on the right. Label small, medium, and large. Now my 2 possible sides would be BD and DC. So then I'm just taking a look between those 2, between BD and DC. DC is the smallest because it's small, medium, large. So again, you can't just take the smallest angle from the whole picture. You have to look at each individual triangle and compare. Similarly for our other one, but we end up finding that this was 65, so it was the same as that guy, and this angle here was 30. So when we have 2 angles that are the same, the sides opposite are also going to be the same. So I just went and labeled as small, medium, medium. You could say small, large, large, whatever you want. And then same thing over here, we had another one of those. What type of triangle is that when 2 of the sides are the same? Isosceles. What's a blah 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 blah? What's a scalene?
No sides are the same.
No sides are the same. No sides are the same for a scalene. And then what's our last one?
Equilateral, all sides are the same.
Equilateral, all sides are the same. Good. Okay. So we have basically 2 isosceles triangles here. So we actually have 3 potential candidates for our smallest side. But again, ZY and ZX are the exact same because they were opposite of the same angles. So I'm just going to compare my ZX and my WX. So I'm just comparing these guys. And the triangle that contains both of them is going to be ZWX. And the smallest of those is WX. So again, Do it one triangle at a time, and then compare your sides from there. All right. Do we have questions on anything from our warm-up? Awesome. So today we get to dive into some of the meatier part of our unit, and I would like for you to get out your vocabulary sheet that you did a few classes ago. That will help us out in what we're doing today.
Cool.
What are we doing now? No, it's a vote. Alright, is there anyone that did not get, let me pull it up here for you, our Unit 7 Day 4 notes? That one. Okay, so again, taking a look at our vocab. Let's see if that's for the right vocab up. Here we go. So taking a look at our vocab, we previously went through, oh thank you. We previously went through and described perpendicular bisector, angle bisector, medium, and altitude. But we did not talk about these guys. Circumcenter, incenter, centroid, and orthocenter. Notice each one has been indented. So what I would like for you to do is just take about 30 seconds with your shoulder partner. Just kind of compare what you've got for each one and make sure we are clear on what a circumcenter is, incenter is, centroid, and orthocenter. Go.
I don't know about that, but it's one that you said magic item. Look at it, show the specs beyond it.
How long do you
Well, it depends on how good your character is, so like with the scope to change anything. I There we go. So then these guys are talking to this one a little bit further. We can take a look at it sometime not during class.
Okay.
Wait, do you look somewhere else?
You shift your focus.
Why do you do that? Oh, you look at the back.
It's kind of like
I see it.
That's gonna just make it up in anything.
What?
Okay. So we have circumcenter, incenter, centroid, and orthocenter. Now, like I said, this unit has a lot of vocab, and this is a great unit to have flashcards with because you need to know which terms, not only what do the terms mean, but which terms go with which other terms. So, refresher, concurrent lines and point of concurrency. Who can explain their own words? What does it mean when lines are concurrent? Yeah, they all intersect at one point. And that particular point we call the point of concurrency. Now, for each set of lines that we have here, perpendicular bisector, angle bisector, median, and centroid, we have that they do meet up at a single point, and their single points are the indented words, circumcenter, incenter, centroid, and orthocenter. On our notes for today, you'll see it says points of concurrency, that's that intersection point. We're looking at specifically perpendicular and angle bisectors today. Next class, we will take a look at the other two, medians and altitudes. So right now, we're taking a look at basically these guys. So it's important that you know that the circumcenter is where your perpendicular bisectors meet up, that your incenter is where the angle bisectors meet up. All right, so let's go ahead and take a look at that portion of our notes. So before we dive into what the theorem actually says, the point of concurrency of the perpendicular bisectors of a triangle is called what?
Circumcenter. Give me a moment. It's G number 6. Already? First period is wrong. I'm telling you, it's the start of the day that the smart board is struggles. It's like some other people I know.
Doesn't like second period or first period.
Yeah, it doesn't like first or second. Okay, circumcenter. Okay. So where all perpendicular bisectors meet up in a triangle, we call this circumcenter. So when we take a look at our picture here, I have my perpendicular bisectors, perpendicular bisector, perpendicular bisector. How do I know these are perpendicular bisectors, besides the fact that I just said they were?
Okay. It bisects one of the sides
Good?
and it makes right angles.
Good. So we've got the notation that's bisecting, and that's right angle. What would we call this point Z?
Midpoint.
It's a midpoint. Good. Same with Y, same with X. Those are midpoints of the sides. Good. Okay, so they all meet up, they crisscross at the same point, our circumcenter. So that's point P there. Okay. So that is called our circumcenter. Now, our concurrency of perpendicular bisectors theorem is going to tell us a special property about our circumcenter. So our theorem says the perpendicular bisectors of a triangle, perpendicular bisectors of a triangle meet at a point what's that point called again?
Circumcenter.
Circumcenter, good. Perpendicular bisectors of a triangle meet at a point called our circumcenter. And here's the special characteristic of it. That is equidistant. That is equidistant from the vertices of the triangle. From the vertices of the triangle. Perpendicular bisectors of a triangle meet at a point, the circumcenter, that is equidistant from the vertices of the triangle. So in other words, the circumcenter is equidistant from the vertices. Now, when I'm saying the vertices, what are the vertices of the triangle?
The vertex.
The vertexes, okay. What's that?
Where the two sides intersect.
Good. Where the two sides intersect, or like the corners. What color do I want? Yeah, stick with red. Yeah. All right, so here are our vertices. And according to this theorem, if I go from the circumcenter to my vertex, PB, picked the wrong part of the board to write on. The measure of segment PB is going to be the same from the circumcenter to the other vertex, PA, which is still the same from our circumcenter to our last vertex piece. So where they meet up, call that a circumcenter. And we go from the circumcenter to the vertices, they're all the same distance. Okay. Do I want to wow you today or next class? Let's do it.
Too bad. Prepare yourself. If I take my compass here,
The good old
the
compass.
good old compass, and I set it to that distance. Okay, now bear with me.
Oh, no more glasses. Oh, wait.
Draw a circle.
Oh, wait.
You're about 2 centimeters.
Hey, deal with it.
Perfect circle.
Okay, so what we actually have is that this length, those 3 equal lengths, is the radius of the circle that circumscribes the triangle. So what that means is that the circle is outside of the triangle lays on the circle itself. How cool is that? Circumcenter, circumscribed triangle. Ooh.
They said triangle make up half of the circle.
Is the triangle what?
Make it like, if they're like half of the triangle and then like the rest.
Ooh, that's a good question. I don't know off the top of my head. I'd have to look into it more. That's a valid thought there, though. So that's bonus knowledge. It's pretty cool. Okay, so circumcenter ends up being the center of our circumscribed circle. But more importantly, for our purposes for this unit, it's important that you know the perpendicular bisectors meet at the circumcenter, and its special property is it's equidistant from the vertices. You need to know that those 3 pieces go together. Perpendicular bisectors meet at circumcenter, which is equidistant from vertices.
Just smack them in the middle of the triangle.
That's a great question. UNESCO said, so it's just smack dab in the middle of the triangle? Not necessarily. And that leads us into our next piece, UNESCO. Man, it's like you're reading my brain.
Ah.
So we're going to take a look at triangles in 3 different scenarios. We have acute, obtuse, and right. So these are 3 different ways we can classify our triangles. Acute, all of our angles are acute. Right, there's one 90-degree angle. Obtuse, there's one obtuse angle. For all acute triangles, our circumcenter, here's our circumcenter, will always be inside the triangle. For all acute triangles, the circumcenter will always be inside the triangle. For all right triangles, the circumcenter is on the triangle. And for all obtuse triangles, where they meet up is actually outside of our triangle. I've just written this off the board. Okay. So this is true for all acute, all right, and all obtuse.
Now let's go a little bit further in depth with our right triangle. It not only is it on the triangle, but specifically on this side. What do we call that side?
I
like that. So for a right triangle, it's specifically on the hypotenuse. Okay, so perpendicular bisectors meet at circumcenter. That circumcenter is equidistant from the vertices. Now, yeah, let's do it. It's important that you know the difference on the picture between angle bisectors and perpendicular bisectors, because you will have a lot of markings.
Number 7.
Why make that go away while orienting the board?
Control shift.
Yes. Okay.
Number 7.
This is about pontoon boats, angle bisectors. Okay, so we will often have pictures where there are a lot of markings on it, and you need to know, do they give me angle bisectors? Do they give me perpendicular bisectors? Wait, is it actually an altitude? Is it a median? you'd be able to recognize what the different pieces are. So let's take a look. I've got 3 different pictures here for us. Let's take a look at this first picture. I want you to discuss with your shoulder partner. Did they give me perpendicular bisectors, angle bisectors, medians, altitudes, or more than one? Look at your vocab sheet to help you out. Yes. Do you have your agenda?
I'll give you the whole thing.
I actually want my agenda. I'll give you the super fancy post-it note pass. Here, sir. All right. I'm gonna go to the bathroom. Is everyone good? Oh, yeah. Which one? Do you remember which one? Midsegment 5. So the question was, angle bisector, perpendicular bisector, altitude, medians, or more than one. So again, let's just refresh your memory real quick. Perpendicular bisector has to be perpendicular and bisect. Angle bisector cuts the angle in half. Median goes from vertex to midpoint. Altitude goes from vertex to other side perpendicular. So taking a look at this one, which one or ones do we have here? What do you guys think? Perpendicular bisector and angle bisector. Give me thumbs up if you agree, thumbs down if you disagree.
What if you half agree?
If you half agree, go halfway. Okay. Does anyone think medians or altitudes? Which one?
G.
Sorry, which median or altitude?
Oh, altitude.
Altitude. How about you, Keegan?
Same thing, altitude.
Okay, so we've got, so no one wants medians. We're going to toss that out the window. Okay, I'm throwing out medians as well. So let's investigate, see what we've got. So let's just go down the list. Our first thing, perpendicular bisector. Perpendicular bisector has to be perpendicular and bisect. All right, so let's look and see. Perpendicular, woohoo, perpendicular, woohoo, perpendicular, woohoo. Bisect?
No.
That's good.
Do they tell us it bisects that side? No. Does it bisect this side?
No.
Does it bisect that side?
No.
So it's actually not perpendicular bisectors. These are not perpendicular bisectors. Let's move on to angle bisectors. Angle bisector must cut the angle in half.
Yes.
Cuts the angle?
Yes.
Yep. Cuts the angle? Yes. Cuts the angle. Good. So we have angle bisectors here. And then we said no way, Jose, to medians, so let's potentially look at altitudes. This one's a little bit kind of harder to see. Altitude goes from vertex to side opposite perpendicular. If I were to take a line here, go from vertex to side opposite perpendicular. Is that actually the same line right there? No, those are two different lines. If I were to go and try to do the perpendicular here as well. Notice these are actually two different lines connecting. So this is also not our altitude. So all we have here is angle bisector and then some weird other perpendicular thing drawn in. So this is actually just angle bisectors. The main thing I wanted you to see is that these were not perpendicular bisectors. That's a common mistake people make, is they assume it's been bisected when it hasn't been. So just watch out for that. Okay, so with that being said, how about this guy? Does this have perpendicular bisectors?
Yes.
Awesome. Does it have angle bisectors? No. So again, be careful. We don't know the angles of them bisected.
It's like what? It's like you're sure this
So we have perpendicular bisectors here, no angle bisectors. Do I have medians?
No.
Nope. So medians again go from vertex to midpoint. That would be a median. Do I have altitudes? Nope. Again, these are two different lines here. So altitude would be more like that. Okay. And then how about this guy over here? What do we have here? Angle bisectors. Do I have perpendicular bisectors for this one?
Altitude.
Oh, we can have
Altitudes.
You have altitude.
Yeah.
Looks like,
We have M and X.
I think it looks like altitudes, potentially.
Potential.
I'll go for it. Altitudes. Medians? No, because again, we don't know where the midpoints are. Okay. So with that being said, these are the common mistakes that people make where they look at it and assume that things are cut in half when we don't know that. So just keep it. So our theorem that we just learned, again, perpendicular bisectors meet at the circumcenter. Its special property is that it's equidistant from the vertices. So, taking a look at the problems that we just did, we said this one is actually perpendicular bisectors. So it says to find the measure of px. What would the measure of px be? Oh, man. Nathaniel?
13.
13. How'd you know it was 13?
Because CP is one of the lines in the all are the same.
Good. So from our circumcenter P, because that's where our perpendicular bisectors met up, from there to our vertices, they're all the same. So I can know if this is 13, this is 13, and this is 13. Awesome. Now, suppose I instead asked you for something like this. Let's call it W. How would I find W? Talk with your shoulder partner. How would you find W? You don't have to actually find it, but just how would you go about it?
WY is half.
So 5 is talking about this length here.
Oh, yeah.
So
No, she was 13. He whatever it is.
all right, I'm gonna bring it back up front. 2 magical words for this guy. How do we find W? What's that, Noah? Yes, Pythagorean theorem. Pythagorean theorem applies to what kind of triangles? Right triangles. Which, looky here, we've got a right triangle. So we just use Pythagorean theorem, 5 squared plus w squared equals 13 squared, and then go from there. What's 13 squared?
109.
What's 14 squared?
196.
That's my favorite. Okay, questions with that? All right, those right triangles, they just sneak up all over the place. Okay, so that goes back to our theorem here. Again, perpendicular bisectors meet the circumcenter, equidistant from the vertices. So once you've established that circumcenter, you can know it's the same distance to the corners. Okay, now we're not always going to have a nice picture given to us with some links. We're going to have this on graphs. Whoa! So coordinate geometry is just when we have our geometry on a coordinate plane. And it says find the circumcenter of the following triangles. Just a reminder, circumcenter comes from perpendicular bisectors. Okay, so example 1, they've conveniently given us the picture, but it's on a coordinate plane. Now, our circumcenter is where all 3 perpendicular bisectors meet up, right? But when I'm trying to find the intersection, I really only need 2 of them because 2 lines will intersect at that point. The third one will just also go there. So we don't have to actually find the perpendicular bisector for all 3 sides. We just need 2 of them and then find where they intersect. Now, for number 1, it's actually one of our easier options because since we only need 2 sides, let's just choose the 2 sides that are easiest to do a perpendicular bisector. Before we do that, just a reminder, perpendicular bisectors have to be perpendicular and they have to bisect. So if it's perpendicular, if I have my slope, what do I have to do to it to get it perpendicular?
Opposite reciprocal.
Good. So I want opposite reciprocal slope. Opposite reciprocal slope. And if it bisects it, what point bisects the segment? That point called the midpoint. So we know it's going to go through the midpoint. Which, oh, how convenient. Don't we have a formula for the midpoint?
Yes.
What? Unit 1 coming back? So our midpoint formula, remember, it's the sum of our x's divided by 2, sum of our y's divided by 2. Okay, all that to say, since we get to choose which 2 sides we're going to perpendicularly bisect, I choose this side and this side. Those are the easiest to write the equation for my perpendicular bisector. Because if I have a horizontal line, what's perpendicular to a horizontal line? Vertical. And if I have a vertical line, what's perpendicular to a vertical line? Horizontal. If I've got a diagonal line, I have to do some more work. I have to find my slope, then do opposite reciprocal. So I'm just choosing to go and do my perpendicular bisectors for these 2. Alright, so this first one over here, let's get the vertical one. That's pretty easy. I can pretty easily find my midpoint even without doing the formula, just looking at my graph. Would you guys agree my midpoint's right about here?
Yes.
So here's my perpendicular bisector cutting through. And we need the equation of it. We need the equations of our perpendicular bisectors. What's the equation of this blue line that I just drew?
Y equals 2.
Y equals 2, very good. Okay, a little bit trickier. Where is my midpoint for this horizontal range?
3.5. No, wait, 1.
2.5.
2.5.
2.5.
Yes. It's on the x-axis.
And I'm hearing conflicting answers. Top it, someone nearby you. Is it 2.5, 3.5? Is there an ish on there? Do we have an actual value?
It's like
Yeah.
1 over 1. It's like 3.5. Yeah, 3.5.
Okay. I think most people finally decided 3.5.
Yes. We don't have.
So I see there's 1, 2, 3, 4, 5 blocks separating. Half of 5 is 2.5. But we didn't start at 0.
Plus 1.
So 1 plus 2.5 gets us 3.5. Made it. Okay, so let's go and draw our perpendicular bisector for that. And what would be our equation of that perpendicular bisector?
X equals
X equals 3.5. Good. So we need to find where they intersect. Where they intersect is where they both occur at the same time. What would be the point?
3.52.
Good. So our circumcenter. Circumcenter. You know what it says. Okay. Is going to make the point 3.5, 2. Super nice when it's a right triangle, oriented in such a way we can just do our vertical and horizontal line, and we immediately get our x and y. Now, it's not always going to be a right triangle. It's not always going to be a nice vertical and horizontal line. So let's revisit that world of Algebra 1 that you loved so dearly. And let's suppose I had one of my equations was, I don't know, y equals 2x minus 5. Maybe that's one of my perpendicular bisectors that we come up with. And we find another perpendicular bisectors equation, and that one was y equals negative 5/3 x minus 8. How do I find where those intersect? No calculator? Okay. Don't use it. Yes, keep it.
Can't you use point
You're thinking too hard. Think algebra 1. How do I solve where these intersect? It's called a system of equations.
Oh, yes, just.
Oh,
okay.
okay.
I didn't use elimination, substitution. Use substitution for that.
Good. So solving a system, finding where these two intersect. You can do either substitution or elimination. The third way was graphing, but that only works when they're nice whole numbers. So we would want to do either substitution or elimination. I'd probably go substitution with this. Totally. So just a reminder, if it's an actual equation, we have to do some substitution. Now, for the problem that we just did, it was nice, straightforward. Here's our x bar, here's your y bar. But that's not always the case. Okay, so let's take a look at example 2. Now, example 2. You can sketch a graph if you want. You can just go ahead and work with the points, however you so desire. We get to choose which two sides we want to do the perpendicular bisectors for. I'm going to go and just do a quick little sketch, just to give you an idea of what I'm working with. 1, 2, 3, 4, 5, 1, 2, negative 1, 2, and negative 1, negative 3. Oh, wait a second. What type of triangle is that? Oh my. It is a right triangle. Now, obviously we can see this from our drawing, but how can I have seen that from my coordinates? What do we notice about our coordinates here? Keegan?
Two like coordinates share an x coordinate and two coordinates share a y coordinate.
Good. We have x's repeated. So that's our negative 1, 2, negative 1, 3. That gave us our vertical side. And we had y's repeated. So 5, 2, and negative 1, 2. Gave us this horizontal side. So if you recognize that from there, awesome. If you have to draw a picture, that's fine. But what that helps us to know is that we should expect our circumcenter to be on the hypotenuse, right? Just like we had over here. Our circumcenter was on the hypotenuse. We should expect it to be on our hypotenuse at first. It also means that it's going to be easier for us to decide which sides to do. Again, I'm going to choose my vertical and horizontal side to do my perpendicular bisectors. So let's go do perpendicular bisectors. We need to know where that midpoint is. You might be able to count it from your graph depending on how nicely you drew it, or just calculate it by hand. It's not too bad. So I'm going to start off with side AB. So my midpoint, I'm just going to operate from my values here. 5 plus negative 1, 4 divided by 2. 2 plus 2, 4 divided by 2. So our midpoint's 2, 2. Okay, so I'm going to go to somewhere about there. Oh, looks like a midpoint. Okay, so if it goes through that, I've got a horizontal line. Vertical is what's going to be perpendicular. So what's my equation for the perpendicular bisector here? So I draw that in. Yeah, x equals 2. Alright, because we know it's a vertical line. Okay, so I'm just going to repeat. Let's do it for side BC. So again, my midpoint, now I'm looking at these guys. Negative 1 plus negative 1 is negative 2 over 2. 2 plus negative 3 would be negative 1 over 2. So my midpoint here would be negative 1, negative 1 half. Somewhere around there. Now, my perpendicular bisector is going to be a horizontal line. So what would be the equation for this guy?
Y equals negative.
Good, y equals negative 1. Alright, so these are my two perpendicular bisectors. So what is the point at which they meet? What's my circumcenter going to be? 2 and
2 negative.
Your circumcenter is 2, negative 1.
So you
Just put it like that.
Yeah, you can put negative 1.
wait, how do you know which x to take from which?
So I have to basically look at my picture here. AB is a horizontal line. I want the perpendicular bisector, so it's going to be a vertical line. Vertical line is x equals.
So that's why I chose my X there. And then vice versa, I will have vertical, I want horizontal line, horizontal line is y equals. It's just,
Do they sometimes give you the midpoint of one side?
they might, yeah.
Of like the one we were just trying to solve for? Can they give you and then you have to find the other midpoint?
The
to make this
other,
one true?
the other endpoint, or you mean,
Yes, yeah, like,
they might, that's probably going a little further than I would expect.
uh,
Okay, so when it's a right triangle, we have this nice shortcut that it's going to be on the hypotenuse, but we also have the shortcut where we have, oh, it's a vertical line, horizontal line. Those are easy equations to write out. I'm going to show you an even shorter shortcut for this. Can you believe it? I'm so nice. We need a shortcut for the shortcut. Okay, so we said that it lands on the hypotenuse, and this is only for right triangles, but it lands on the hypotenuse. Let's just take a look at example 2. Which side is my hypotenuse, for example? AC. So taking a look at AC, I would like for you to find the midpoint of side AC. Midpoint of side AC. Alright, so we've got 5 plus -1 is 4. I have a 2. 2 plus -3 is -1. I have a 2. Did you guys get 2 -1/2? How convenient. So when it's a right triangle, our circumcenter will actually always be the midpoint of our hypotenuse.
Where do we use that to check?
You can always, yeah, you can always use it to check. So if you remember that shortcut for the shortcut, you can just recognize it's a right triangle, do your midpoint and hypotenuse, and be done. If you forget, you can go back to drawing it out in your equations. Okay, so right triangles, super nice. Let's take a look at a non-right triangle. So flip that over to the back side. Time to go to Farmer John. I made up the name. It's actually Farmer Dave. My neighbor was Dave. Farmer Dave. Okay. So it says, where should the farmer place the hay bale so that it is equidistant from the 3 gates? Notice we don't have a right triangle here. But we have to actually do some work. Good. It's good to exercise your brains. Now, it doesn't ask anything about the circumcenter. But I know that I need to find the circumcenter. How do I know that?
That's the vertexes of the triangles are the gates, and we have to find the point which is equidistant. And by the concurrency of perpendicular bisectors theorem, the point on the circumcenter is equidistant between the vertexes.
Good. It's asking to have equidistant from the gates. Our gates are our vertices. So it's asking what's equidistant from the vertices. Well, the theorem that we just learned is that the circumcenter is equidistant from the vertices. So this indicates to me that I actually want to find my circumcenter. Again, I cannot emphasize to you enough how important it is that you know what these terms mean and what goes with what, so you can know what it's asking about. So we actually want to find our circumcenter. Again, we need 2 perpendicular bisectors. We're going to write the equation for 2 perpendicular bisectors. You get to pick which 2. I'm going to go ahead and choose to use this side. That one's easy to find. And then I'm just going to go with side AB just because I have to. So I need 2 perpendicular bisectors. So I'm going to start with side BC. Where's my midpoint? Oh, nice. 0.
0.
And it's a horizontal line, so my vertical line, x equals 0. Boom, we've already got one of our perpendicular bisectors. Awesome. Okay.
I need to do more work for the other one now. Okay, so keep in mind, perpendicular bisector. We have that it bisects, so it meets at the midpoint, and it's perpendicular, so I want my opposite reciprocal slope. We need those two things. Because for an equation of a line, I just need a point and a slope. Well, my point would be the midpoint, and my slope would be the perpendicular slope. Okay, so let's go and take a look at side AB and find that information we need. So I need my midpoint. Not quite so easy to count from here, so let's just go and take a look at our points. We had, what, 0.30 and 0.5. So let's find our midpoint. 0 plus 3 is 3 divided by 2. 5 plus 0, 5 divided by 2. Alright, so there's my midpoint for side AB. 1.5, 2.5. Okay, I'm going to approximately mark where that is. Just for visual sake, we don't actually need that. And then I'm just going to go ahead and approximately draw my perpendicular bisector, just so again I have an idea of what's happening. Okay, we need to know our slope before I can do perpendicular slope. So I need my slope of AB. Again, you can either count or use the points. I like counting. 1, 2, 3, 4, 5. 1, 2, 3. So negative 5/3. Do you guys agree with that first slope? Oh, that's, I said 5/3 and we're at 5/5. So my slope for side AB is negative 5/3. My midpoint for side AB is 3/2, 5/2. Questions as to how I got this information? Okay. So my perpendicular bisector needs to go through this point, and it needs to have the perpendicular slope. So let's just go and write out our perpendicular slope. What would my perpendicular slope be?
3/5.
3/5. So for my perpendicular bisector, I'm going to be using this and this. Okay. So I have a point in the slope. I'm just going to use point and slope form. So y minus 5/2 equals 3/5 times x minus 3/5. Y minus 5/2 equals 3/5 times x minus 3/5. Okay. So not too bad. We now have an equation for a perpendicular bisector, a little more complicated of one, and another equation for a perpendicular bisector. Pretty easy one. So we've got two equations. Now we just need to do substitution or elimination in order to solve. I'm giving you a substitution because we already have x is 0. So all I have to do is take this, put it in for x. So Stoner system using substitution. Y minus 5/2 equals 3/5 times 0 minus 3/2. Ooh, fractions galore. A great time for you to practice your fractions. I want you guys to go ahead and solve for y. What do you get? Adding, subtracting, multiplying fractions. Whew. What am I doing making you think this hard on a Thursday? Go and check your answers with someone nearby you. See how you did with your fractions. Fractions are your friends.
Wait, should that get?
What's that? It ends up being a fraction.
I want you to check the shortcut and we'll find out. I've heard two answers so far. I want you comparing with someone nearby you. Yeah, if you want to. You still have to deal with fractions. Right?
It's less complicated than one of those. Watch.
You'll be fine. This? Our homework will be on this stuff. Yeah. I was like, we don't have much left. All right. Revisiting fractions. Multiplying. We've got adding, subtracting. Have to get common denominators. So far, I heard 8 over 5. I heard 12 over 5 or 12 over 10. I heard 17 over 10. 8 over 5. Other thoughts?
Oh, yeah.
3 over 5. Sounds like most of us at least like the denominator 5.
Yes.
The answer is
Stop screaming in my head.
Yes.
8 over 5. Okay. So just refresh our fractional memory. So we have y minus 5 halves equals 3 fifths times negative 3 halves. How do I multiply fractions? What do I do?
Numerator by numerator and multiply the denominator.
Multiply straight across. Good. So y minus 5 halves equals negative 9 tenths. Now you could have multiplied both sides by 10 to get rid of it, but to make you practice fractions, I'm going to go and add 5 halves to both sides. Now I normally would not do this. I would multiply to get rid of that fraction in the very beginning. But we need practice with fractions. In order to add them together, I have to have the same denominator. How do I get a common denominator?
2 by 5.
Good. And we have to multiply both top and bottom by that. So we actually have negative 9 tenths plus 25 tenths.
Which will equal 16.
16 over
10. Now, again, I would have personally probably multiplied by 10. But it's good for us to practice fractions. Okay, so all that to say, our answer was 8 fifths. Let me write that out. Okay, so we have x equals 0. We have y equals 8 fifths. Our circumcenter is that point. 0, 8 fifths. Again, you can see that would not have been so easy to try to guess it on your graph. So we did have to actually write our equation line. So we found one perpendicular bisector that was nice and easy. Found your other perpendicular bisector equation. We needed our midpoint, slope to opposite reciprocal, then just match them together. Now, if it's a right triangle, use the shortcut. But when it's not, we'll get to some. Okay, questions with that? So that was all with perpendicular bisectors. They meet at the circumcenter, which is equidistant from the vertices. The other thing we're going to look at today is angle bisectors theorem. And you'll notice there is no coordinate geometry after this.
Oh, no.
So we will not be doing angle bisectors on a coordinate plane, because do you have a way to figure out how to bisect the angle on a coordinate plane?
No.
So we will just always have pictures for this.
Yeah.
Yay. Okay. So let's go and write out our concurrency of angle bisectors theorem. It's going to sound pretty familiar. The angle bisectors of a triangle. The angle bisectors of a triangle. The angle bisectors of a triangle meet at a point Oh, what's that point called again?
Incenter.
Incenter. Incenter. That is equidistant. That is equidistant from the sides of the triangle. From the sides of the triangle. The angle bisectors meet at a point, incenter, that is equidistant from the sides of the triangle. Oh, I forgot to make us fill this in.
Incenter.
The point of concurrency of angle bisectors is the incenter.
That's all for today.
Hold on, we're not done yet. There's still stuff we have to write and draw. I wish we could go home. I wish it was Friday. Alright, so our incenter is where the angle bisectors meet up. So here's angle bisector. Here's an angle bisector. Here's an angle bisector. This guy is my incenter.
It is the dotted line in the shirt.
So what's with this whole perpendicular dotted stuff? Because it makes us think there's perpendicular bisectors when there's not. It says that it's equidistant from the sides. So again, angle bisectors, the incenter, its special property is equidistant from the sides. When we are talking about going from a point to a side, that distance is always the shortest distance, which is our shortest perpendicular distance. That's why that's perpendicular is drawn in, to indicate that we're talking about the shortest distance. We didn't go, haywire and go off to the side. So that perpendicular is there just to indicate that's the distance from the point to the side. So our conclusion for this guy would be, P is still the incenter, so PX, measure that. It's the same as the measure PY, which is the same as the measure PZ. Okay. So for this guy, oh man, super important piece here. Our incenter is always inside the triangle. Always inside the triangle. The incenter is always inside. Now, time for some wow.
Another step.
So, our equidistant piece, it's going to become a square. Our equidistant piece is from the incenter to the side. So, if I set my compass approximately to the incenter to the side. We're just gonna go with it.
No.
It won't let me go in between. It jumps. It's not possible to go smaller.
No
Then move the compass backwards, then like the thing.
That's good. That's good.
But that's no. I don't want that one. I want this one. Okay. Pretend it was perfect.
No.
Then this would be.
So close.
It is so close. So frustrating.
Extend circle a bit.
Yes.
Okay, you don't see me fudging this.
Okay.
So our incenter is actually the center of the inscribed circle, which is the circle inside the triangle. So incenter is the inscribed circle. Circumcenter is the circumscribed circle. Oh, you think we're done? Yeah, you want the homework. You wish you were getting the homework.
We want the homework.
No, you're getting homework. All right, what's the measure of PM?
How do you know that?
Equidistant to the side.
Such a fun.
Okay, so your homework is the back side of 3 and worksheet 2. Worksheet 2 is what's coming to you.
What is this?
Worksheet 2.
The map, yes.
Back side of 3. Oh, yes, there's the
We're gonna do. Wait, there's no number.
Well, I don't think they have
Problems up.
You should. Yeah, it should be.
It's not